Shri Gurubhyo Namaha, children. Hope you went through yesterday's concepts. What is that we were discussing? We were discussing about resistivity. Now, resistivity, and we were also discussing on limitations of Ohm's law. So, this is what we were discussing yesterday. Today, we are going to continue with resistors. Now, we were talking about resistors. Now, resistors are nothing but it resists the flow of charges in a circuit. Okay. Now what for we use this resistors? Resistors are used in connecting electrical circuits. Okay. Now, as such, resistors are concerned, commercially produced resistors that are used in domestic, that mean used for domestic purpose and used in labs. There are of two major types. One is wire bound resistors. The second one is carbon resistors. Okay, now we are going to see much more in detail about carbon resistors. But before that, when we talk about this wire bound resistors, now these resistors are made by winding the wires of an alloy. Alloys in the sense, for example, manganese, nichrome, combination of metals, you call it as alloy. Nichrome is a combination of nickel and chromium. So these alloys are these alloys are wounded. Okay, wounded and actually this is based on their temperature. Now, as these alloys are insensitive to temperature and the resistors are made using this, and the range of these resistances are to a maximum of a few hundred ohms, which are considered to be very, very small. But whereas when you consider carbon resistors, now the range of these carbon resistors are higher enough, and these resistors are made up of carbon, which are considered to be compact, and they are not much expensive. It is very easy to go for carbon resistors, and they are also small in size. When you come to the school, I'll be probably show you how a carbon resistor looks like. And in fact, I'll share some pictures. Now we are going to discuss on that, and I'm going to show the picture of how a carbon resistor looks like. Okay, so they are very small in size, and you can find out the value of resistances in a carbon resistor using color codes. Okay, now here is a tabular column which talks about the resistor color codes of a carbon resistor. Now look at this. There are so many colors here, children, which is the first column: black, brown, red, orange, yellow, green, blue, violet, gray, white. Now this is the colors. Now the resistors can be made up of any of the combination of these colors. Now this is the color order, and each color has been given a number, right? So black is given 0, brown is given 1, red 2, orange 3, yellow 4, green 5, blue 6, violet 7, gray 8, and white 9. Now to remember the order of this color, let me have a common code for this. You can easily remember this. Now I will write here B.B. Roy. Okay, B.B. Roy of Great Britain. You remember this sentence, so you will not forget this color code and color and the number. B.B. Roy of Great Britain had a very good wife. Okay, remember this. B R O Y G B V G W. Okay, so look at this. Compare now. Black, brown, red, orange, yellow. That is B.B. Roy. Then Great Britain, G and B. Great Britain had a very good wife, VGW. So remember this sentence, and you will have these colors and their respective numbers, and the number starts with 0, children. Don't forget that. 9 colors, 10 colors, so you have 0 to 9. Okay, ma? So it is a easy sentence. You can easily memorize this. Baby Roy of Great Britain had a very good wife. To remember the color and their number. Okay, right. Now, how do you find out the resistance of these resistors? Okay, I have given the color, the number is given, and the multiplier. Now, whenever you have, I will tell you how this is used. And you have for the resistors, at the end you have 3 rings, which is gold, silver, and some rings will not have any color. If the ring is going to be gold, it has got tolerance of 5%. If it is going to be a silver ring at the end, then it will have 10% of tolerance, and if it is going to be no color, then you will have 20% of tolerance. Now let us go to a carbon resistor. How can we find out the resistance of a carbon resistor? I am going to discuss 2 examples here, children. Now this is how a carbon resistor looks like. A very small size. You have 2 leads on the either side. This is made up of carbon, and you have colored rings here. Now as far as this is concerned, you have 3 rings. Now listen here. This is the first ring, second ring, third ring, and the fourth ring will be of either gold, silver, or it may be without any ring. Now as far as this diagram is concerned, it is a silver ring, children. Okay, so this last ring talks about tolerance. Okay, so the first ring is red color, right? So what is the value of red? The value of red is 2, right? So first number I will write. Now look at the second ring. The second ring also is red in color. Okay, so for the first 2 color, you will exactly write the number. Okay, ma? Now the third ring is again a red color. Instead of writing the number, you will write the exponent of it into 10 power. What is the color of red? It is 2. So again I will write it as 22 into 10 power 2. Okay. This is the value of the resistance. And what will be the tolerance? Tolerance will be plus or minus. Now what is the fourth ring? Fourth ring is the silver color. Now this gold, silver and no color represents the tolerant rate. Okay, so since the color is silver, what is the tolerance of silver? Tolerance of silver is 10%, right? So it is plus or minus 10%. So this is the resistance of the resistor. This is the value. Is it clear? This is how you will, based on the colors, you will be able to find out the value of the resistance of these type of resistors. Now let us go to this. Okay. Now here the combination is yellow, violet, brown. Okay. So what is the value of yellow? Yellow is 4. Okay. So 4. Then violet. Violet is 7. So we'll write the first 2 colors. For the first 2 colors we will write the number. And for the third color we will take the exponent. And what is that color? Brown. So what is the color number for brown? Number for brown is 1. So it is 10 power 1 ohm plus or minus. What is the ring here? Last ring is gold. So gold tolerance rate is 5. Yes. So plus or minus 5%. Now 10 power 1 is 1. So I can have the value as 47 into 10 ohm with plus or minus 5%. So this is the tolerance, this is the resistance of this resistor. Okay. Are you able to understand? So if any resistor with some colors are given, you should be able to find out the value of resistance. Clear? So this is about carbon resistors, right? Next, we are going on to a very, very important topic, which is called as temperature dependence of resistivity. So, how the resistivity varies, okay, with temperature. So, The topic itself is named as temperature dependence of resistivity, or we are going to arrive at some formulas here, which I will be discussing. Okay, so the topic is, let me write the heading, temperature dependence, temperature dependence of resistivity. So the resistance of a conductor, or the resistivity of a conductor, or the resistivity of any material, okay, it depends on temperature. So resistivity is rho, children. Rho has a dependence on temperature, right? So what happens to the resistivity when you increase the temperature? Temperature varies, right? So if you are going to increase the temperature, the resistivity of a conductor will also increase. Now this can be given by an equation. Rho of T is equal to rho naught into 1 plus alpha, I will write here, children, alpha T minus T naught. Now this is the expression. This is how I will write it once again very clearly here. Rho of T is equal to rho naught into 1 plus alpha T minus T naught. So what are these terms here? Of course, rho T is the resistivity of a conductor at any temperature. Rho naught is the resistivity of a conductor at some reference temperature. Let us take the value as 20 degree. Usually we will take it as 20 degree. So which is considered to be the reference temperature. Now this is with respect to some particular temperature. Let us take it as 100 degree. Now this is the reference temperature. This is the instant temperature. And what is this alpha? Alpha is nothing but, this is a very important term here, children. Alpha is nothing but, you call it as temperature coefficient of resistivity. Okay. So this is nothing but, it is defined. Now this is defined as ratio of alpha is defined as, I'll write the formula, the ratio of increase in resistivity. Increase in resistivity is rho T minus rho naught divided by per degree rise in temperature to its resistivity at T naught. So I will have T minus T naught. Now this is the formula for alpha. Alpha is defined as the ratio of increase in resistivity per degree rise in temperature to its resistivity at T naught. So this is the definition for resistivity. Now these formulas are not there in your textbook, children. They have given a formula. The formula given in your textbook is rho T is equal to, this formula is given. This formula is given there in your textbook, but you should know this also. And I am also going to give one more formula based on resistance also. So please make a note of these formulas when I send the link. Okay, so this is the definition for temperature coefficient of resistivity. This is a very, very important term, children. And so problems will be based on this definitely. So what happens to the resistivity when you increase the temperature? So definitely resistivity, when you increase the temperature, resistivity also will increase, which is given by this formula. And what is alpha? Alpha is nothing but temperature coefficient of resistivity. Okay, and the unit for this is unit for alpha, I will write here, alpha is represented as per degree centigrade, which is the unit for temperature coefficient of resistivity, per degree centigrade. Okay, now let us discuss this alpha for conductors and semiconductors. Okay, so that is the graphical representation here, right? Now for conductors, whenever we talk about conductors, this alpha, that is the temperature coefficient of resistivity, is considered to be positive. Now, if you increase the temperature of a conductor, definitely what happens to the kinetic energy of electrons that are there in the conductor? Definitely the because electrons are considered to be moving charges. So when you increase the temperature, that will increase the average kinetic energy of the electrons there. Yes or no? So the average kinetic energy of electrons is increased. Now what happens? That will increase the collision in the sense we talk about tau. Okay, tau is nothing but two successive collisions. What about the average time? The average time will be reduced because the collision starts taking place at a faster manner because the temperature is increased. So you have more amount of frequent collisions taking place between the electrons and the positive ions, and the average time, which is nothing but tau is nothing but the average time of two successive collisions. That is what we discussed, relaxation time. So the average time of collisions will be decreasing. If it is going to be decreasing, then the resistivity will increase. Now that is shown in the graph. Now this is the resistivity of copper as a function of temperature. It is increasing. Look at the graph. It is almost a linear curve because when the resistivity is when the temperature is increasing, to the x-axis we have drawn the temperature, to the y-axis it is resistivity, right? So when the temperature is increasing and the resistivity is also increasing. Okay, now it varies linearly, but for alloys, now look at the second graph, children. Now this is a graphical representation for an alloy. As I told you, nichrome, here they have explained for nichrome. Actually here for alloys, there also exists a non-linear. Now this is a linear region. Now here the graph is a straight line. This is a linear region, but this starts with some basic value of resistance. Are able to understand? Here the basic value of resistivity is considered to be 0, whereas here it is not 0. It starts with some value, right? There exists a non-linear region at very low temperature. Now here the temperature is very low, right? Now they have a value for resistivity, and after that when you keep on increasing the temperature, the resistivity will increase. Okay, now you can this is the second graphical representation. And we also talk about resistivity equal to resistance. Yes or no? When length is 1 meter and area is 1 meter square, we say that resistance is equal to resistivity. So this formula can also be given in terms of resistance. In terms of resistance, I will write the formula as RT is equal to R naught into 1 plus alpha T minus T naught. Now what I have done, I have just replaced resistivity in terms of resistance. The same formula here, whatever I have given here, rho T is equal to rho naught into 1 plus alpha T minus T naught. Similarly, RT is equal to R naught 1 plus alpha T minus T naught. Now this is in terms of resistivity, this is in terms of resistance. Okay ma? So because we know that resistance is directly proportional to resistivity, so I can have this formula also. Okay, are you able to understand? Yes? Yes or no? Okay. Now let us go to the next case where we talk about alpha of semiconductors. Now semiconductors, we know that the resistivity of a semiconductor decreases with increase in temperature. That is what we discussed in the second volume. We have already completed this topic, semiconductors. So when the temperature is increased, the resistivity decreases. So you have more number of electrons that are liberated from the atoms, and the current increases and the resistivity decreases. This is the case of a semiconductor. Now this is called as negative temperature because the temperature increases, the resistivity is decreasing, so you call it as negative temperature coefficient of resistance. Okay. Now this principle works in thermistor. Okay, you have temperature, negative temperature coefficient of resistance for a thermistor, which is an example for this. Whenever you increase the temperature, the resistivity will decrease in the case of a semiconductor. Okay, now we know the formula for electrical conductivity. What is the formula for electrical conductivity? Electrical conductivity or resistivity is equal to 1 by sigma, right? So 1 by sigma is can be written as m by n e square tau. Okay. Now from this we can relate. Now I can also write sigma to be, what is sigma now? Sigma will be n e square tau by m. Now compare this. Now sigma is nothing but, what is sigma? Sigma is nothing but conductivity. So I can just relate that resistivity of a material. Now resistivity here it is rho equal to 1 by sigma, which is equal to m by n e square tau, right? Now when we compare the resistivity of the material, the resistivity, when I talk about resistivity, I can have this formula rho equal to m by n e square tau. So the resistivity of a material, now it has got an inverse proportionality with n and also with tau. So what is n, children? N is nothing but, you know what is n? N is nothing but the number density of electrons per unit volume. So the resistivity is inversely proportional to the number of electron density, and also it is inversely proportional to the average time between the collisions. Okay, so in a metal, if the temperature increases, the tau decreases, and in semiconductors, when temperature increases, tau decreases, but the overall resistivity also decreases here. So you have to be very familiar with these concepts, children. Have a snapshot of it if you want, or when I share the link, please make a note of all these things. Now all these formulas are involved in solving numerical problems. Okay, so with this we'll go to the first numerical problem. At room temperature 27 degrees Celsius, the resistance of a heating element is 100 ohm. So R1 is given as 100 ohm. What is the temperature of the element if the resistance is found to be 117 ohm? So R2 is 117. So what is happening to the resistance here? Initially it was 100, then it is turned to be 117, because in that case the resistance is increasing. Okay, and they have given the value of alpha to be, what is the value of alpha? Alpha is 1.7 into 10 power minus 4 degree per Celsius. And the room temperature is T1, okay, which is given as 27 degrees Celsius. So what is that you should find out? You should find out T2. Okay, what is the temperature of the element if the resistance is increasing by 117? So you need to find out the value of T2. So let us write the formula based on resistance, because all the resistance values are given. So let us write alpha equal to R2 minus R1 by R1 T2 minus T1. I have rearranged the formula here. Look at this thing. I have rearranged this formula and I have written like this. Okay, you can rearrange and see. Now substitute. I want the value of T2. So that term alone you bring it to the left side. So T2 minus T1 will be there. As such, the other terms R2 minus R1 divided by denominator you have alpha into R1. Alpha will come to the right side. This T2 minus T1 will go to the left side. Now substitute the values, children. R2 minus R1, it is 117 minus 100 by alpha value is 1.7 into 10 power minus 4. So the resistance at room temperature is 100, right? So substitute, you will have the answer to be 1000 here, which is the temperature difference. But I want T2. Okay, so T2 will be 1000 plus T1, right? So 1000 plus what is T1 is 27. So T2 will be 1027 degrees Celsius. So when the temperature is increased to 1027, what happens to the resistance? The resistance is also increasing. We discussed this only. When the resistance is, when the temperature is increasing, the resistance also increasing. Now initial temperature is 100. Initial temperature is 27. Now the temperature is raised to 1027, though resistance also is increased from 100 to 117. Okay, hope this concept is clear, right? We'll move on to the next sum. A silver wire has a resistance of 2.1 ohm at 27.5 degree. So R1 is equal to 2.1 ohm at T1, which is equal to 27.5 degree centigrade. Okay, next, and a resistance of 2.7 ohm at 100 degrees. So R2 is 2.7 ohm at T2 equal to 100 degrees Celsius. Okay, so what is happening here? Temperature is increasing, resistance also increasing. By the values itself we can find out, right? Now what is that? You should determine the temperature coefficient of resistivity of silver. So you have to determine the value of alpha. So again write the formula: alpha equal to R2 minus R1 divided by R1 T2 minus T1. Okay ma? Right? Okay, now substitute 2.7 minus 2.1 divided by R1 is again 2.1 into T2 minus T1. T2 is 100 minus 27.5. Am I correct? Yes. So what is 2.7 minus 2.1? It is 0.6 divided by, I have 2.1, 2.1 into what is 100 minus 27.5. 100 minus 27.5 will be 72.5. Am I right? Yes or no? Yes. 9 minus 7. Yes, 72.5. And you have the answer for alpha to be 0.00394 degree per Celsius. So this is the temperature coefficient of resistivity of silver. Is it clear, children? Yes? Are you understanding? So two topics we have discussed today, children. One is the color code for carbon resistors. The color code for carbon resistors, which takes the short form of B.B. Roy of Great Britain had a very good wife. Now you have to remember this tabular column very clearly. Only then you will be able to find out the value of resistance. Okay? And to find out the value of resistance, the first two colors will be given their respective numbers, and the third color will be written as the exponent power of the color. Suppose if the third color is red here, so it is 10 power the number of the color. Similarly, in the second diagram, the third color is brown, so it is 10 to the power of the number of the color is 1. So with plus or minus, the fourth ring talks about the tolerance rate. Tolerance rate, if it is gold, it is 5, if it is silver, it is 10, and if there is no color, sometimes you will not have any ring here at all. So in that case, you have to take the tolerance to be 20%. So with the tolerance, you will be able to find out the value of the resistance of carbon resistors. Okay? And next comes temperature dependence of resistivity. I have given the formula. Whenever you increase the temperature, the resistivity and the resistance of the conductor will increase. In the case of conductors, the resistance will increase. In the case of semiconductors, when you increase the temperature, the resistance will decrease. So we have discussed two formulas. based on resistivity and based on resistance. For resistivity, we have given the formula to be rho t is equal to rho naught 1 plus alpha t minus t naught. Now this alpha is nothing but you call it as temperature coefficient of resistivity, and the unit for alpha is per degree Celsius. Okay, so when I rearrange this formula, I have the formula in terms of resistivity, and I have written the formula in terms of resistance, which is RT is equal to R naught into 1 plus alpha T minus T naught. Now I have compared the dependence of resistivity with the number density of electrons, which is called as electron density, and also with average time collision, which is called as relaxation time. Okay, so these are some of the very important formulas that we have discussed, and go through the sums that I have done. You have many more problems of this, which will be the two problems that I discussed are from the textbook itself, children. These problems are there in your textbook, which I have solved. So please work out the problems. We'll be continuing with the next chapter tomorrow, children. Okay, see you then. Bye.